Hello, everyone. I'm Olympia. Thank you for being here with me in this wonderful place called Lights Out Library, and I have a great story to tell you. I'll take you on a new space journey tonight, but contrary to other journeys we made to other planets, stars, or even galaxies, the objects of our attention tonight will be much smaller. I'll tell you about asteroids, comets, and the phenomenon of shooting stars, meteors, when small asteroids and meteors enter and travel through our atmosphere. We have a lot to discover. Our cruise will begin in the upper layers of our atmosphere, and then, following the trail of these bodies, we will travel through the solar system, through the asteroid belt, and even beyond the orbit of Neptune. I will also tell you about different phenomena like how comets form, why and how bodies burn through our atmosphere, what a comet's tail is made of, and I'll also tell you about Oumuamua, this strange space object that was detected a few years ago and probably comes from another system. But first, I would like to take a few seconds of your time to let you know that we have a Patreon page for those of you who wish to and can support this project, get more from it, and listen ad-free on your favorite podcast app. Patreon is a platform that allows you to contribute directly to our work financially. If you join, you will gain access to various new features. For example, you will have the option to listen to all our episodes with or without background sounds and receive regular bonus episodes. We already offer 9 exclusive episodes to our patrons, the latest one about the Colossus of Rhodes. This is the second wonder of the 7 wonders of the ancient world that we will explore, and once completed, they will all be edited together to create a 4-hour story. In addition, you will have the capability to download all these audios and participate in selecting future topics. We also offer advance releases and updates on upcoming episodes. We hope to see you there soon so that we can continue developing Lights Out Library, which we thoroughly enjoy. You will find a link in the description box and the first comment pinned under the video. As always, you do not need to watch the video to follow along. If you fall asleep and wish to resume the video later, or jump directly to a particular part of the story, timestamps are also listed in the description and pinned in the first comment, as well as links to different streaming options like Spotify, Apple Podcasts, and Amazon Music, which may be better suited for you. We ask that if you can, please subscribe to the channel and click on the like button. This helps us promote the channel and eliminate advertisements as much as YouTube allows us to. But before we begin, if you wish to, you may close your eyes and allow yourself to forget about any worries as we embark on this adventure together. Now, assume a comfortable position. Maybe move a bit to settle. Take a long, deep, relaxing breath, and when you slowly exhale, feel your shoulders drop. Release the tension in your neck. Let your face soften and your jaw relax. Make sure your fingers are not clenched and that your legs are relaxed too. And allow the sound of my voice to guide you through this journey. And now that we're all set, let's get started. Our cruise begins just a few miles above the surface of the Earth, above the clouds, a good place to observe shooting stars at night. You know what they are, a glowing streak of light that travels for a short time in our atmosphere and can sometimes be observed from the surface at night when meteorological conditions allow it. But shooting stars or falling stars are colloquial terms for a meteor. So, what are the differences between these various words? Meteor, meteorite, meteoroid, asteroid, and comet. The differences are all about size, location, and composition. A meteor is synonymous with shooting stars. It is more a phenomenon than an object. The object that causes a meteor is a meteoroid, or an asteroid. The difference between a meteoroid and an asteroid is essentially the size and mass. A meteoroid is smaller, typically the size of a pebble. There is no official precise range of mass for meteoroids. But think about anything from the size of a grain of sand to a basketball. Meteorites are generally fragments of asteroids, which are bigger. A meteorite is what remains of a meteoroid or asteroid after it has fallen on Earth, if it has not entirely fragmented and burned. In summary, an asteroid can break into smaller meteoroids, and if they enter Earth's atmosphere, they generate meteors as they burn. Finally, if something is left of the body after impact with the Earth's surface, it will be a meteorite. A comet is a different type of asteroid. It has a particular composition, which we will examine later, and an orbit, a trajectory in space, that makes it periodically come close enough to the Sun for the interaction of solar radiation with its elements. This interaction generates a coma and a tail of gases and dust, which give the comet its well-known popular appearance. As we are now high in the atmosphere, let's take a look at meteors or shooting stars. They are the same thing. It is not that common to observe shooting stars, which might make us think that meteors entering the Earth's atmosphere are fairly rare. It is actually the opposite. It is estimated that about 25 million meteoroids enter our atmosphere each day. This is about 1 million each hour. Or, to put it another way, since you started listening to this story, about 100,000 meteoroids have arrived. But don't panic, because almost none of them can reach the surface. They are generally no bigger than grains of sand, and they turn to dust long before they could hit the ground. Only big meteoroids visibly catch fire and become meteors. The constant arrival of material that turns to dust and eventually falls to the surface represents a significant volume, about 15,000 tons annually. This means that the Earth gains about 40 tons of material each day due to meteoroids. 40 tons that end up spread more or less evenly as dust on its surface. Why do these meteoroids burn and break apart? As you know, it is due to the density of atmospheric gases. They are heated to incandescence. In the upper atmosphere, the density is sufficient to heat them to incandescence. This creates a streak of light when the object is large enough. It burns and sheds glowing incandescent material in its wake. Shooting stars typically look much closer than they really are. They seem to be a few thousand feet high in the sky, but in reality they essentially occur in the mesosphere, which is 76 to 100 kilometers above our heads. That's about 50 to 60 miles. As you also know, it is Earth's gravity that makes the meteorites fall toward its surface. Sometimes they can be space debris that was in orbit around the Earth and lost enough altitude to enter the atmosphere. But generally, meteors happen because of Earth's motion. As it travels on its orbit around the Sun, it crosses streams of debris, for example, left by a comet or that happened to cross its orbit. This is what causes meteor showers when suddenly plenty of large enough meteoroids enter the atmosphere together and become incandescent due to friction with air molecules. Friction, or in the case of slightly bigger meteoroids, something called ram pressure, causes this heating. So what is ram pressure? When a body moves through a fluid medium like air, it compresses the medium in front of it, causing a drag force to be exerted on the body. In the case of atmospheric entry, it leads to strong heating of the air in front of it. This applies to meteoroids of a certain size, and even more to space capsules or space shuttles when they return to Earth. They were in the void or quasi-void, and suddenly they enter a denser medium with air around them. As they move fast, the air in front of them is suddenly compressed. A shock wave occurs, and this suddenly compressed air heats up due to the compression. This hot air will flow around the object and, in turn, heat it up to hundreds of degrees. It is this phenomenon that heats up meteoroids and makes them burn, rather than friction collisions with air molecules. However, it depends on their size. If their size is big enough, from 3 to 4 inches or 10 centimeters in diameter, ram pressure causes the majority of the heating. When they are smaller than that, friction is the main cause because they are too small to cause enough compression of air in front of them. A practical application of the understanding of ram pressure when objects enter the atmosphere is the design of space capsules or space shuttles. In the first years of space exploration, it was assumed that the best design for an object re-entering the atmosphere, returning to the Earth after a journey to space, would be one with a sharp, streamlined profile that would minimize friction and limit the rise in temperature. But a counterintuitive alternative was proposed: a large, blunt body concept. This is what you see in space capsules that return to Earth. They are shaped as cones. They are conical, and they present their base, which is wider, when they enter the atmosphere. This is because of ram pressure. It is taken into account that, given their size, the main contributor to heating as they fall towards the surface will be the compression of air in front of them. In other words, the transformation of their velocity, their kinetic energy, into heat, not friction with air, is the primary concern. So the question is how to optimize the evacuation of this hot air around the capsule with minimal physical interaction. This is where the conical shape is a good one. The hot air that flows around the capsule does not heat the walls much, only the base. Because the walls recede, they don't oppose much resistance to the air. To a lesser extent, the design of space shuttles is influenced by this. They have a large nose, not a pointed one. Of course, you still need a thermal shield made of material resistant to very high temperatures in the blunt base that will be in direct contact with compressed air. But this design turned out to be more efficient to facilitate re-entry into the atmosphere. Returning to meteoroids and asteroids that fall to Earth, as you know, they are sometimes big enough not to shed all their matter during their crossing of the atmosphere, and so sometimes they impact the surface. They can even be big enough to create an impact crater. Let's take a look at their composition, their size, and in some extreme cases in Earth's history, how their impact can have an effect on the planet as a whole. Meteorites, the remains of a meteoroid, are not that common. Normally about half a dozen to a dozen a year are observed to fall and are recovered for analysis. There are certainly many more that go unnoticed or fall into oceans, but a few dozen meteorites a year is almost nothing when you compare it to the millions of meteoroids that enter the atmosphere every day. Out of these few meteorites, even fewer are big enough to create an impact crater. Most of the time, they are no bigger than a pebble, and they create a small pit. But the possible crater and their size when they hit the surface is not only determined by their mass. A more important factor is what they are made of. Most of the time, impact craters on Earth are caused by metallic iron meteoroids. We will take a look at some of these craters in a minute. These are more resilient to the crossing of the atmosphere. Traditionally, three categories of meteorites have been distinguished. Iron meteorites are one of them. They are largely composed of metal, especially iron and nickel. Then there are rocky or stony meteorites. These are made of silicate minerals, which means that at the atomic level, they consist predominantly of silicon and oxygen. And there is a third category for composite meteorites called stony iron that contains a mix of metal and rock. Most known impact craters were caused by the first category, iron meteorites, because rocky material is easily disrupted in the atmosphere. This includes asteroids or small comets with a mass of several tons. They will break into smaller pieces due to heating and shock waves, and each of these pieces will be reduced to dust. Whereas iron meteorites are more solid. They will still lose much of their mass before impact, but some material may still remain intact. One hypothesis that has gained credibility in the past 10 years or so is that some of the complex organic compounds necessary for life on Earth could have arrived via falling meteorites. They would not have included complete living organisms, but rather large fragments of DNA and RNA that are fundamental to biological life as we know it. Why is this credible? First, because laboratory experiments under outer space conditions have shown that these compounds could form through chemical reactions on asteroids. Some very old meteorites, several billion years old, that we have found on Earth have also been found to contain liquid water. That was not a surprise. It is believed that much of the water we have on Earth arrived via massive asteroid bombardments when the planet was still forming. More interestingly, they also contain prebiotic organic substances, that is to say, some of the ingredients, the building blocks that make biological life possible. So while the idea that asteroids contributed to the emergence of life on Earth sounded like a long shot 2 or 3 decades ago, it is not as unlikely as it may sound. These compounds can form in space, and they can also resist entry into the atmosphere. As we have seen, there is a degree of molecular destruction when meteoroids crash and burn, but compounds may also be dispersed during the fall or preserved inside a meteorite. There are thousands of meteorites in circulation in labs, museums, and private collections, and most of them are fairly small. The largest known one is the Hale-Bopp meteorite, and it fell in Namibia, Africa. It is believed to have fallen sometime over the past 80,000 years. Its mass has been estimated to be more than 60 tons, and it contains about 84% iron. It now has a bit of rust on its surface due to oxidation. The fall of such a big asteroid on Earth would have caused significant damage theoretically, but maybe less than one could imagine in that particular case, because no big impact crater was found where it fell. An explanation could be the way it fell. These are just estimates, but due to its shape, it has been estimated that it slowed considerably during its fall. The entry speed into the atmosphere would have been typically in excess of 10 kilometers per second, about 22,000 miles per hour. But at the time of impact, it would have slowed down to just about 320 meters per second, 720 miles per hour. That is to say, below the sound of speed. This was still probably a violent impact, but at this speed and despite its mass, it would not have created a big excavation. This also probably explains why such a big meteorite could stay in one place. The most violent impacts in the planet's history, it is believed, saw the disintegration of the meteoroid or asteroid because they impacted at very high velocity and they disappeared. Their matter was scattered over a large perimeter and in the atmosphere. In recent history, a much bigger impact event is thought to be the Tunguska event, an explosion that remains somewhat mysterious that occurred in eastern Siberia in 1908. No impact crater was found, likely because the meteorite would have been stony and would have disintegrated at an altitude of 5 to 10 kilometers, 3 to 6 miles up in the air. That would still have been enough to generate a massive shock wave, which flattened the forest over an area of 800 square miles, destroying 80 million trees. In that case, the meteoroid would have been 50 to 60 meters in size, up to 200 feet. Because it happened only a bit more than a century ago, the Tunguska event is the largest recorded impact event in history. Much larger impacts happened in prehistoric times. The largest known impact crater on Earth is in South Africa. It is called the Vredefort crater and is estimated to be 2 billion years old. It is 100 miles wide, and it is believed the asteroid that hit must have been 10 to 15 kilometers, 6 to 9 meters in diameter. As is widely known, it is estimated that an asteroid impact caused, or at least contributed to, the extinction of most dinosaurs millions of years ago, at the end of the Cretaceous. This impact in South Africa is much older, 2 billion years old. Life on Earth would have been only ocean-bound, and the organisms were small. But an impact of that magnitude probably had catastrophic consequences on the whole planet because of the initial shock wave, and then the tremendous amount of dust thrown up into the atmosphere, changing the climate for months to years. It is expected that an object bigger than 1 kilometer across, 0.6 mile, could have global impact, and the one that fell at Vredefort crater was at least 10 times that diameter. The second largest known impact crater is the Chicxulub crater in Mexico on the Yucatan Peninsula. This one is much younger, 66 million years ago, and it is the prime suspect for the extinction of non-avian dinosaurs. That is to say, all dinosaurs minus birds, and also 75% of all species at the end of the Cretaceous period. At the time, the Yucatan Peninsula was under a shallow sea. It was not emerged like today. So now the crater is partially on land and partially underwater. But back then, the asteroid impacted the seabed. Contrary to 2 billion years ago, Earth at the end of the Cretaceous was teeming with terrestrial life. There were giant forests and all types of plants and animal species that were the ancestors of modern species. So the consequences on life, in the case of that impact, were probably much worse than the one that happened 2 billion years ago. First, because of the impact itself, which would have sent a splash of rock and debris into space, and upon their return to Earth, these flaming debris would have torched much of the planet, and then because of a dust cloud that must have enveloped Earth for years, blocking sunlight, causing temperatures to drop and disrupting food chains. Now, this being said, should we worry about such a catastrophic event? Probably not. While it is still possible, statistically, the probability that it happens during our lives or our children's lives is close to zero. There are more serious pressing concerns to worry about. However destructive an asteroid impact can be, it could not really end life on Earth. Life is so diverse. It exists everywhere, including in the depths of the ocean, where it does not need sunlight. It could find a way to adapt and come back. Also, as the solar system ages, the quantity of large asteroid debris flying around on orbits that can cross ours has diminished significantly. All the very big impact craters are also very old. The youngest large impact crater on Earth, which is to say several miles in diameter, is in Tajikistan in Central Asia, and it is already 5 million years old. Now that we have looked at materials and meteorites that fall on Earth, let's leave our atmosphere and head to where they come from, or to the places where asteroids can be found. The official definition of an asteroid is that it is a minor planet of the inner solar system. They are called minor planets because the one difference with planets is their size. Asteroids are smaller. Obviously, there are smaller bodies outside of the solar system. Inner solar system means everything that is contained between the Sun and their asteroid belt, a large region of the solar system located between Mars and Jupiter. But beyond the last planet of the system, Neptune, there is another large belt, the Kuiper Belt, that contains millions of bodies that could also be called asteroids. The only difference with asteroids from the asteroid belt is their location. Let's take a look at the millions of bodies that float in the asteroid belt. Some are fairly big, but the majority range from a few inches to a few feet at most. The asteroid belt is located 2 to 4 astronomical units from the Sun. 1 astronomical unit is the distance from the Sun to Earth, so it is 2 to 4 times farther from the Sun than we are. It is where the majority of independent bodies of that size in the solar system concentrate. So why there instead of being scattered all around? The main hypotheses based on models of formation of the solar system is that these asteroids are the shattered remains of planetesimals, which are bodies that appeared when the Sun was forming by accreting matter. The dust that formed the disk in the early stages of the solar system. All planets of the system would be the product of this accretion. They absorbed all other bodies on or around their orbits through collisions and by attracting them due to gravitation. Actually, as we have seen earlier, this accretion process never ended completely. We talked about how Earth keeps gaining thousands of tons of matter every year due to meteoroids entering the atmosphere. But now the phenomenon is marginal in comparison with what it was billions of years ago. Some of these bodies were satellited by planets, but the majority were swallowed. However, not all planetesimals ended up becoming planets. Some were absorbed by bigger planetesimals, and others were ejected from the system, or at least from the outer solar system, by the gravitational influence of other planets, especially Jupiter. When Jupiter grew and neared its current mass, becoming by far the most massive planet of the system, its influence ejected over 99% of planetesimals in the belt. No planet or large enough body could form in this orbit between Mars and Jupiter. There were still collisions, but no body large enough to absorb the others ever formed. In this model, it is believed that many objects in the belt entered into orbital resonance with Jupiter. If you're curious about orbital resonance, I tell you more about this phenomenon in the story about Jupiter's moons. This would have been what led to their ejection from the inner solar system. Another model suggests that some of the asteroids that are now in the belt could have been captured from the outer asteroid belt beyond Neptune, the Kuiper Belt, and dragged between Mars and Jupiter. So now there would be a mix of bodies, planetesimals that formed there that never became bigger than dwarf planets. For example, Ceres, the largest asteroid in the belt, was big enough to become round and differentiate. That is to say, the heavier elements it was made of, metal, migrated to its core, and lighter elements like rock or water became wrapped around the core. It is believed that Ceres formed in the asteroid belt, but this is not 100% certain. It could also have been one of these bodies attracted from the outer belt. Smaller asteroids would mostly be the remains of shattered planetesimals that did not collide with others to grow more. They stayed small or were shattered by collisions. In any case, we should not picture the asteroid belt as one of those asteroid fields that we sometimes see in sci-fi movies, where spaceships have to slalom between floating rocks. This kind of environment doesn't exist in the asteroid belt. To find something similar, we would have to go inside the rings of Saturn, for example, where there is enough density of floating rocks and ice. We could cross the asteroid belt without even noticing it because it is very empty. There are millions of asteroids, and about 1 million have been identified. They are much more common than in any other part of the inner solar system, but they are scattered over such a vast area that they can have millions of miles between them. Visually, the belt is not dense at all. About 1 to 2 million asteroids would be more than 1 kilometer large in diameter. That's 0.6 miles. And there would be millions more smaller than that. 200 asteroids are bigger than 100 kilometers. These ones have been named, and some of them have been explored by probes. Now, at the scale of the mass of the solar system, the asteroid belt is really not much. It's almost negligible. If we were to put all the asteroids together, we would get only 3% of the mass of the Moon. And one body alone, Ceres, accounts for 40% of the belt's mass. Ceres is the only body of the belt large enough to be round. The next ones are classified by mass, like Vesta or Pallas, are irregular because they are too small for their internal pressure to make their components melt, and they never took on a round shape. The surfaces of Vesta and Pallas show that they collided with other asteroids in the past, as evidenced by their craters. Although collisions can still happen in the asteroid belt today, they have become rare events. Because of the large distances between asteroids, collisions have become unlikely, and most of the time, except when involving Ceres or Vesta, they will not lead to accretion. These bodies are relatively small and don't have much gravitational pull, so instead they are more likely to shatter asteroids into smaller pieces. However, not all asteroids are located in the asteroid belt. There are other locations. First, there are asteroids called Trojans. They share their orbit with a larger planet or moon, but don't collide with it because they have reached points of equilibrium and stability that make them orbit always at the same distance ahead of or behind the larger body. Jupiter has many of these Trojans. Maybe more than 1 million larger than 1 kilometer are thought to exist in Jupiter's orbit. Unless a perturbation occurs due to another body, They will not collide with Jupiter because they always maintain the same distance. They are positioned in two groups, one ahead of and one behind Jupiter. Mars has 9 identified Trojans, and Earth has 2. The largest one is 1.2 kilometers, 3/4 of a mile, wide, and was discovered in 2020. The other one was discovered in 2010. These are both recent discoveries, and the second one is 300 meters, almost 1,000 feet in diameter. They are both hundreds of times more distant than the Moon. They could be less costly to reach in terms of energy because they are on the same orbit as our planet, by definition. They are small, but one day in the distant future, they could be a valuable source of rare elements that are technically present on Earth, but are very hard to access. For example, iridium, a very dense metallic element. There is iridium on Earth, but due to its density, it mostly sunk to the core of the planet shortly after its formation. These asteroids may have a similar composition to Earth, rock and metal. But since they are much smaller, it could be easier to access these rare elements on them. Beyond the asteroid belt and Trojans, there is also a smaller number of asteroids on orbits that pass close to planets. As of today, if we take Earth as an example, almost 30,000 near-Earth asteroids have been identified. These are the ones that are most observed for the possible hazard they represent. Their orbits are typically unstable because they are perturbed by Earth's orbit. Most of the time, this will result in their ejection from the solar system or a collision with the Sun, a planet, or another body. Of course, it is extremely unlikely that a collision will happen every time they complete an orbit. But given millions of years and millions of orbits, it will eventually happen. For that reason, these near-Earth asteroids survive in their orbit for just a few million years. There are still thousands of them because they keep arriving. It is believed that they generally come from the asteroid belt. The orbital resonance with Jupiter makes them migrate towards the inner solar system closer to the Sun, where they come nearer to the terrestrial planets like Mars, Earth, or Venus. A small number of near-Earth objects are also thought to be extinct comets that can no longer produce a tail because the elements that produce the tail have all been consumed. As we can see, there is a wide variety of asteroids, and contrary to the orbits of planets, they have remained fairly stable for billions of years. These asteroids are subject to various influences that can make them change position in and out of the solar system. These celestial bodies transit and travel, and we now know that they can move between star systems. Let's talk about Oumuamua, an object that attracted much attention in recent years. Because of its shape and origin, it is likely to be extrasolar. The shape is elongated like a cigar, and it measures between 100 and 1,000 meters, 300 to 3,000 feet. Oumuamua is a Hawaiian name because it was detected from an observatory in Hawaii. I mentioned earlier that objects, asteroids, may be expelled from the solar system. We discussed this when we spoke about the influence of Jupiter. But this does not make them disappear, of course. If they leave our system, they will travel in space, and eventually they can reach another star system, even though space within the galaxy like ours is mostly void. Star systems are very distant from one another. Typically, the distance has to be expressed in light years, but statistically, ejected objects will end up crossing the path of other systems that can include planets. We know that some planets are not bound, no longer bound to a star, and travel alone in space. Oumuamua is not very big compared to common asteroids in our system. We saw earlier that more than 1 million asteroids in the asteroid belt could be larger than 3,000 feet, and Oumuamua barely enters this category. But what revealed its origin is that it did not travel on a sun-bound orbit. It entered the system on a trajectory and with an initial velocity that prevented it from being captured. This meant that it would cross our system and then continue its journey. When it was first observed, it was only 0.2 astronomical units away from Earth. That's pretty close at the scale of the system, only 85 times as far away as the Moon. When it was spotted, it was already heading away from the Sun. Another thing that drew attention was that when it approached the Sun, it exhibited an acceleration that was not due to the Sun's gravitation. This was weird. It could have suggested that it produced its own thrust, but this wasn't unexplainable by natural phenomena. The Sun may have influence on other bodies beyond its gravitation. It can provoke outgassing, which we will discuss when we cover comets, or it can push things away due to radiation pressure. Of course, between the shape of Oumuamua, its extrasolar origin, and its trajectory and acceleration, it raised the question of possible alien technology. Could it be an interstellar ship? Though that would be a strange shape, and its surface appears red and similar to natural objects in the outer solar system. So it does look like a natural body, despite its unusual shape. A small number of astronomers suggested that Oumuamua could be a product of alien technology. They didn't definitely state this was the case, but noted that the phenomenon was unusual enough and difficult enough to explain to warrant attention. The majority believe that it is a natural object, and there are several hypotheses about how it formed. It could be a remnant of a disintegrated exoplanet, a comet from outside the solar system, or a piece of an exoplanet from beyond our solar system. But it is true that this particularly strange object will probably continue to draw attention in the coming years, as it is still inside the solar system. Now, let's talk about a particular type of body that is similar to asteroids, but with a few distinct characteristics: comets. As of today, there are more than 4,000 known comets in the solar system. Their most obvious difference from asteroids is that they can sometimes be seen from Earth with the naked eye, because they create a long, luminous tail in their wake. Why is that? How do comets work in general? The center, the nucleus of a comet, is hardly distinguishable from an asteroid. It is a loose collection of agglomerated ice, dust, and rock. The term ice here does not only refer to water ice like on Earth. In astronomy, ice is the term for compounds that are often found solid in space due to the low temperature, but that are volatile. They can be readily vaporized. It can be water, but astronomical ices also include carbon dioxide, nitrogen, ammonia, methane, sulfur dioxide, and others. All of this is contained inside the nucleus of a comet. Some comets are small and measure a few hundred meters across. Others are giant and measure tens of kilometers or miles. Like everything in the solar system, comets follow an orbit. But this orbit is highly elliptical and eccentric. Instead of revolving around the Sun at almost always the same distance, like Earth, for example, Earth does not have a perfectly circular orbit. As you know, at some moments of the year, it comes slightly closer or slightly farther from the Sun. But the difference in distance is comparatively very small, whereas comets can be 10 or 100 times farther from the Sun when they reach their most eccentric point than when they are at their least eccentric point. We will see later that the type of orbits they have and the frequency of their returns near the Sun depends a lot on where they come from. But the big specificity they have is that when they approach the Sun following their orbit, solar radiation and the solar wind warm the ices they contain. Because they are volatile, they separate from the nucleus. They are released. This is the phenomenon called outgassing. These gases, water vapor, carbon dioxide, methane, also take dust with them and generate a kind of atmosphere around the nucleus. This atmosphere is called a coma, and it reflects enough sunlight to be visible from afar. This coma is not bound by gravitation to the nucleus because the nucleus is not massive enough for that. So it can visibly stretch behind the nucleus over long distances, up to 15 times the Earth's diameter. It would disappear quickly if it was not renewed by the continuing effect of the Sun's proximity. These are basically volatile elements ejected from the comet's nucleus. The coma dusts appear when the comet has passed near the Sun and starts to move away on its eccentric orbit. Once it is far enough for the ices to stop outgassing, the coma goes away. It disappears, and the nucleus returns to the appearance of a regular asteroid that will continue on its orbit and will stay without a coma for years, or up to hundreds of years, depending on how long it takes to return near the Sun on the comet's particular orbit. But the most visible part of a comet that passes close to the Sun is not this coma, actually. It is the tail. The tail is a second section of gas and dust from the nucleus that is blown out from the coma by the Sun's light pressure and the solar wind. A stream of tiny particles that the Sun constantly emits. The tail will typically be even longer and more visible than the coma. It can stretch beyond 1 astronomical unit, more than the Sun-Earth distance. The tail is typically what we picture comets with, as comets consume some of their matter to produce their coma, and their tail every time they pass near the Sun. They have an expiration date. The nucleus will end up exhausted once it can no longer outgas, and it will keep revolving around the Sun until it changes orbit. but as a comet asteroid, a dead comet. The solar system has existed for billions of years already, and yet there are still active comets. How is that possible? They should have died long ago. This is possible because there is a giant reservoir of potential comets beyond the orbit of Neptune, in the Kuiper Belt, and even more beyond it in a spherical cloud of icy bodies that extends beyond the Kuiper Belt, called the Oort cloud. It is believed that these potential comet nuclei can be seen in motion in the Kuiper Belt by the influence of planets, and in the Oort cloud by gravitational perturbations at the scale of the galaxy, for example, the passing of other stars. If their orbit is modified and brings them close enough to the Sun to start outgassing, they become comets. So depending on where they originate, there are short-period comets that need a few decades to complete an orbit, and long-period comets that need much more time. The reservoir of comet-like bodies in the Oort cloud is estimated to be 1,000,000,000,000, 1,000 billion. This is why, with only a few thousand active comets at any given time, we will never exhaust this stock of potential objects. The solar system will disappear long before. The way comets work has been studied and quite well understood for decades. More recently, probes have visited them, which is quite an achievement given their speed and small size. A probe called Deep Impact, sent by NASA, blasted a crater on a comet called Tempel 1 and photographed it to study its interior. Another probe, Rosetta, sent by the European Space Agency, was the first to land on a comet and send information from there. Not all comets stay bound to the solar system. As I mentioned earlier, there are objects that can travel between stars. This happens if the trajectory of a new comet does not allow it to form an orbit around which it will keep traveling. These are called hyperbolic comets. After one passage near the Sun, they are ejected from the system and may or may not reach another system one day, where they will deploy their tail again if they come close enough to another star. Some of the most famous and expected comets include Halley's Comet. It is named after Edmund Halley, the publisher and friend of Isaac Newton. Using Newton's work, he realized that the comets sighted in 1531, 1607, and that reappeared in 1682 were in fact the same body, not three different bodies. Calculating its return and taking into account the perturbations the comet would sustain from the gravitation of the planets, he forecasted the comet would reappear in the sky in 1758. Indeed, it reappeared in December 1758. The comet has a period of 75 to 76 years. It varies slightly each time due to the effect of the more massive planets in the system, like Jupiter or Saturn. The last visible passage of Halley's Comet was in 1986, and it is expected to return by mid-2061. This comet was also the first to be observed in detail by spacecraft during its 1986 visit to the inner solar system. A lot of hypotheses about how comets work were validated thanks to these observations, especially the prediction that the comet's nucleus would be composed of a mix of rock, ice, and dust that we discussed before. Dirty Snowball was the name given to the hypotheses that comets were made of such elements, and it was outgassing that liberated the coma and the tail. When this comet is not in the inner solar system, it returns to the Kuiper Belt. It goes beyond the orbit of Neptune at a distance of 35 astronomical units, roughly the distance of Pluto from the Sun. It reaches its farthest point from the Sun. This point is called the aphelion, and then it starts coming back. Overall, it takes about 75 years to complete one orbit. Comets are classified as short period when their orbital period is under 200 years, so Halley is a short period comet. Above 200 years, there are long period comets. A famous example of a long period comet is Hale-Bopp, which became visible in 1990s and was one of the brightest seen for decades. Hale-Bopp has an orbital period of 2,500 years, so needless to say, we won't be alive to see it again. Its aphelion, the farthest part from the Sun, is at 370 astronomical units. That's 10 times farther than Halley's comet. It has a much longer orbit and comes from the Oort cloud. It stayed visible for 18 months in the 1990s, so we have plenty of photographs that show the coma and tail very well. As of 2022, Hale-Bopp has already crossed the orbits of Neptune and even Pluto's. It is traveling in the Kuiper Belt and will keep moving away from us for more than 1,000 years before beginning its travel back, after centuries spent in the silence and darkness of space, where the Sun is only a tiny point on the horizon. We have come to the end of our little journey tonight, but I will be back with another story soon. I hope you enjoyed this adventure, and I invite you to discover and learn more. Now you can let go and sleep. Or if you're not sleepy yet, you may pick another story from my ever-growing library. And until we meet again, good night. Sleep well.